Triglycerides to biodiesel, chemical conversion explained. Triglycerides to biodiesel, chemical conversion explained. In the quest for sustainable energy sources, biodiesel has emerged as a promising alternative to conventional fossil fuels. Biodiesel is a renewable and environmentally friendly fuel derived from natural feedstocks, such as vegetable oils and animal fats. One of the key processes involved in producing biodiesel is the chemical conversion of triglycerides, the main components of these feedstocks. In this article, we will delve into the fascinating world of triglyceride to biodiesel conversion, exploring the chemical reactions and technologies that make this transformation possible. Understanding triglycerides, building blocks of biodiesel. Triglycerides, often referred to as fats or oils, are complex molecules composed of glycerol and 3 fatty acid chains. They are naturally found in various plant and animal sources, including soybean oil, canola oil, and even recycled cooking grease. The structure of triglycerides is crucial to their conversion into biodiesel. This chemical reaction breaks down the triglycerides into their constituent components, glycerol and fatty acid methyl or ethyl esters, which are the building blocks of biodiesel. The overall reaction can be represented as follows. Triglyceride plus alcohol glycerol plus fatty acid esters, biodiesel. Transesterification, the heart of biodiesel production. Transesterification is the cornerstone of biodiesel production, and several factors influence the success of this chemical conversion. One crucial aspect is the choice of catalyst. Catalysts are substances that accelerate chemical reactions without being consumed in the process. In transesterification, catalysts are used to facilitate the breakdown of triglycerides and promote the formation of biodiesel. 2 types of catalysts are commonly employed: homogeneous catalysts and heterogeneous catalysts. Homogeneous catalysts are soluble in both the reactants and the products, while heterogeneous catalysts are insoluble and exist as separate phases. Sodium hydroxide, NO, and potassium hydroxide, CO, are examples of homogeneous catalysts frequently used in transesterification. These catalysts are highly effective in promoting the reaction, but they require careful handling due to their corrosive nature. Heterogeneous catalysts, on the other hand, offer certain advantages such as ease of separation from the reaction mixture, reduced waste generation, and potentially milder reaction conditions. Solid acid catalysts, such as zeolites, have shown promise in transesterification reactions. Research is ongoing to develop more efficient and environmentally friendly catalysts for biodiesel production. The role of alcohol in transesterification. Alcohol plays a crucial role in transesterification by reacting with the triglycerides to break them down into biodiesel and glycerol. Methanol and ethanol are the most commonly used alcohols in this process. The alcohol reacts with the triglycerides' fatty acid chains, resulting in the displacement of the glycerol backbone. The newly formed biodiesel molecules are then separated from the glycerol and other byproducts. It is important to note that the choice of alcohol can impact the efficiency of the transesterification process. Methanol, for instance, is more commonly used due to its lower cost and faster reaction kinetics. However, ethanol is a more sustainable choice as it can be derived from renewable sources such as sugarcane or corn. Reaction conditions and optimization. The success of transesterification relies on careful control of reaction conditions. Temperature, pressure, and the molar ratio of alcohol to triglyceride are critical factors that influence the yield and quality of biodiesel. Typically, the reaction is carried out at a moderate temperature, 50 to 70 degrees Celsius, and atmospheric pressure. The molar ratio of alcohol to triglyceride is important as it affects the extent of the reaction and the yield of biodiesel. An excess of alcohol helps drive the reaction toward completion, but an excessively high ratio can lead to increased production costs and difficulties in separating the products. Finding the optimal molar ratio is a balance between maximizing biodiesel yield and minimizing alcohol usage. Purification and byproduct management. After the transesterification reaction, the mixture contains biodiesel, glycerol, unreacted alcohol, catalyst, and other impurities. Efficient separation and purification techniques are crucial to obtain high-quality biodiesel. The first step involves allowing the mixture to settle, which causes glycerol and biodiesel to separate due to their differing densities. The glycerol can then be removed, and the remaining mixture is washed to remove residual catalyst and impurities. Vacuum distillation is often employed to remove any remaining alcohol and traces of glycerol, resulting in a purified biodiesel product. Challenges and future directions. One significant challenge is feedstock availability. The demand for biodiesel has led to concerns about potential competition between biodiesel production and food production. To address this, researchers are exploring non-food sources of triglycerides, such as algae and waste oils, to ensure sustainable and ethical biodiesel production. Additionally, efforts are underway to develop more efficient catalysts and reaction conditions that minimize energy consumption and waste generation. Enzymatic catalysts, which offer greater specificity and milder reaction conditions, are being investigated as a greener alternative to traditional catalysts. Innovations in biodiesel production. As the demand for biodiesel continues to grow, researchers and engineers are constantly working on innovative approaches to improve the efficiency and sustainability of biodiesel production. One promising avenue of research involves the use of supercritical fluids in transesterification. Supercritical fluids, such as supercritical methanol, have unique properties that can enhance the reaction rate and reduce the need for catalysts. Operating in a supercritical state, fluids exhibit both liquid and gas-like properties, which can lead to faster mass transfer and improved reaction kinetics. This approach has the potential to simplify the biodiesel production process and reduce the energy input required. Another exciting development is the integration of transesterification with other processes, such as hydrolysis and esterification. Hydrolysis involves breaking down the glycerol byproduct into valuable chemicals like glycerin, which finds applications in various industries.